Hello and welcome to this episode of the Industrial Engineering Notebook. Today's topic is elementary row operations. Eventually, I'd like to get to a point where I can do videos on matrix equations, which means we need to understand how to take the inverse of a matrix, which means we need to understand elementary row operations. This is one of the first things that you'll learn in linear algebra. All things considered, I don't think it's too difficult. It's kind of like solving a little puzzle. So let's dive in. Let's say we have a system of equations, and that's going to look something like this. So we have three equations that all use three different variables, and each variable affects each outcome with a different weight. We want to know what values of x1, x2, and x3 would satisfy all three of these equations. And because the number of variables that we have equals the number of equations that we have, we know there's going to be a single answer, which is great. So we're going to put this system of equations in the form of a matrix. So if there's no coefficient up here, then we just consider that a 1. So plus x2 plus 1 times x2, so that's why that ends up being a 1. And then there is no x2 in this first equation, so we would say it's plus 0x2 is kind of in there. So negative 2, 0, 8. And then this column right here is just what's on the other side of the equal sign. And it'd be really great if we could mix up this matrix just enough so instead it looked something like this. Because writing this as a system of equations, it would mean x1 equals whatever, x2 equals whatever, x3 equals whatever. This is the answer we're looking for. So to do this, we're going to do some operations to this matrix. We're going to start by just trying to put zeros here, and then eventually we'll want zeros here, here, and here, and we're going to want these to all be 1. So let's look at some of those operations that we can do. There are 3 total. First, you can swap rows. Pretty self-explanatory. Next up, you can scale, and that's where you multiply each element in a row by a constant. So take a row and then multiply everything by 1/3 or by -3 or something like that. And finally, the most important one is scale and sum, where you add a scaled version of one row to another row. And we'll see this one in action. So this is the matrix. Remember, we want 1s on this diagonal, and these little triangles we want to be 0s up here. The first thing I'm going to do is work on getting this to be a 0, so we're going to want to scale and sum. So if we could get this 1 to be -3, and then we added -3 to +3, then this element right here would be 0. So we need a scaled version of row 3 that we add to row 2. Scale and sum it is. -3 times row 3 plus row 2 is going to yield our new row 2. Nothing changed about row 1. Nothing changed about row 3 either. We're just adding a scaled version of this to row 2. So row 2 is definitely going to change. -3 times 1 is -3 plus +3. Remember, we had a +3 over here. So that's going to give us our 0. -3 times -1 is going to be +3. And we'll add that to +1, which is 4. -3 times -5 is +15, plus 1 is 16. -3 times -18 is +54, plus 14 is 68. Cool, and we have the 0 here, which is what we wanted. And red feels pretty boring right now, so I'm going to switch to blue. As we look at this third row here, we want this to be a 0. So if we look at row 1, what's a scaled version of row 1 that we could add to row 3 to give us a row 3 that has a 0 here? Well, -2 times 1/2 would be -1, and -1 plus +1 would be 0. So 1/2 times row 1 plus row 3 is going to yield our new row 3. Row 1 didn't change. Row 2 didn't change. Okay, row 3. So 1/2 times -2 is -1, plus 1 is 0. 1/2 times 0 is 0, plus -1 is -1. 1/2 times 8 is 4, plus -5 is -1. 1/2 times 26 is 13, plus -18 is -5. Okay, I think you get scale and sum now. And frankly, I like this blue color much more than that red color, but we're going to switch to green. The next thing that we can do is get a 1 here, because remember we want 1s on this diagonal. So I'm just going to scale row 1. Not scale and sum like we've been doing up here, just a regular old scale. -1/2 times row 1 is going to yield our new row 1. Purple feels appropriate for the next color for some reason. Next, we want to scale and sum again, so we want this to be a 0, which means we're going to need to multiply this by 1/4 to get us 1 plus -1 is going to be 0. And this operation is going to give us this matrix. Cool, so we got zeros here. We're going to put a 1 here. To do that, we're just going to scale the second row by 1/4. And I want a 1 here, so we're going to scale the third row by 1/3. And to start putting zeros up here, things are going to be a little bit easier because we have these rows with a bunch of zeros in it. So it doesn't really matter what you scale these by. Anything times 0 is 0. So if you use the third row for a scale and sum operation, you won't have to worry about undoing the work we did here or here. -4 times row 3 plus row 2 is going to give us our new row 2. We're so close to the end. We have zeros in this triangle. We almost have zeros in this triangle, and we already have 1s in the diagonal. We're going to use row 3 again because these zeros are super convenient. And the last operation we're going to do is 4 times row 3 plus row 1 to yield our new row 1. And this was our goal. 1s in the diagonal, zeros in this triangle, zeros in this triangle. This column was the column for the coefficients on x1. So this first equation here now says x1 equals 3. Second equation says x2 equals 1. Our last equation says x3 equals 4. So there's our solution. And you could have found that without all this linear algebra stuff. Right? You could have tried plugging and chugging and moving these equations around and substituting and all that. But that can get messy. This is much more systematic. And it's an easier example. There are much harder examples, some that don't always have unique solutions, some that have many solutions, some that have no solution. But this is the basics. Understanding this means we can go on to understand what the inverse of a matrix is, and if we can understand the inverse of a matrix, we can understand all those fun engineering equations that have matrices in them. If you like this video, go ahead and hit the like button. If you want to see more videos like this, please hit the subscribe button. And if you have questions, feel free to leave them in the comments.